Yeah, circle the axis going. Okay, then what's my next step going to be? Yeah, treat the diode as an open. So I just kind of remove it from the circuit. Then I'm going to bring my soft voltages down. And what am I going to measure for voltage at this point?
No.
It's always going to take it first to be 10 volts.
Yeah, but
Series now.
yeah. So now we have a little bit. Now we have a.
It's 700 millivolts. But it's an open, it'd be 5 plus 5 volts.
Okay, so R1 is 10 ohms, right?
Oh, sorry.
Yep.
9 volts.
And then R2 is 100 ohms. So without the circuit in there, what kind of a circuit do I have in there?
Series.
Series circuit. What's another name for a series circuit?
Voltage divider.
Voltage divider. So what am I going to have to do? I'm going to have to divide up my voltage, right? So I got to divide up my voltage across R1 and R2 to get my soft voltage. So what's my voltage going to be across R1?
9 volts.
No.
What's the other way around?
Oh, crap.
Okay, which one always drops the most amount of voltage?
The smallest resistor.
The largest.
Largest resistor.
Largest one always drops.
Can't be 1 volt then.
Yeah.
No. Because we know that this one has to be,
Yeah.
this one's going to have to drop how many more times voltage than this one?
10 times.
10 times. So if this one drops 1, this one drops how, and this one has to drop the remainder, 9, right? Is that a 10 to 1 ratio?
No.
It'd be, across R1 would be 909.1 milliamp, or millivolts, excuse me.
So 900 and
909.
909.1.
909.1
milliamp.
millivolts. And then R2 would drop what?
9.091 volt.
1 volt.
Yeah.
There you go. Now we got a 10 to 1 ratio, right? This one is 10 times more than this one. Yeah. All right. So now we have our. Now we should let's. I'm gonna change that to red here. So we'll keep all our soft voltages to red. So these are all just soft voltages for now. So we'll keep all our soft voltages red. All right, so what's going to be my soft voltage then at my anode side? So which way is we should probably put in let's put in our current paths too. So we know that I got a plus 10 here, and my reference is here, so right, so I know that my current is going what, north to south or south to north?
North to south.
South
South to
South to
north.
north. Okay? So we know my current is going that way. So now what is going to be my soft voltage then at my anode?
Positive 9.091 volts.
Right. So it's going to be a positive 9.091 volts. Then what's going to be on my cathode side?
Plus or minus 0.
Plus or minus 0. Okay? So now we determine whether that diode is a go or no go. So is that diode a go or no go? It's a go. So it's going to be a go. And it's going to take its voltage first, just like it always does. So my voltage across the diode is going to be what? 0.7 volts. Okay? We know that this is more negative than positive, and so our polarity is the correct way there. All right, so we know that the diode is going to be will go, and it's going to drop 0.7 volts. So then what is going to be my voltage across R2 then?
0.7 volts.
0.7 volts. Because R2 is connected to D1 by how?
Parallel.
By parallel. What remains constant in a parallel circuit? Voltage. So then we know that R2 now is going to drop, and it's going to drop down to 0.7 volts for R2. So what's going to be my voltage across? Let's see. So we got our R2. So what's my voltage out going to be then?
0.7 volts.
Yep. And don't forget the polarity though. Positive 0.7 volts or 700 millivolts. Positive 0.7 volts. What's my voltage across R1 going to be?
That changes.
9.3 volts.
9.3 volts. It's going to be the remainder amount of voltage. Yep. So that's going to drop the remainder amount of voltage, so whatever way I go, so if I start out here, I know if I go from here to here, I'm going to measure a positive 10 volts. So just to verify that, no matter which direction I go, then I'm going to go positive 9.3 plus another positive 0.7 equals my 10 volts. Or if I even went down, first sign I see is positive 9.3, go down this branch, positive 0.7, I'm going to get 10 volts. So either way, I'm going to get my 10 volts. So we always just want to verify that. Okay. So what's my current of R1?
930 yeah, milliamps.
Yeah, 930 milliamps. Okay. What's my current of R2?
Is that like 700 nano micro amps? Yeah, 7 milliamps.
7 milliamps. Yeah, so R2 is going to have 7 milliamps. What's my current going through D1 then?
923 milliamps.
923 milliamps. Because another name for a parallel circuit is what?
Current divider.
Current divider, right? So we have D1 and R2 that are in parallel, but is in series with R1, right? So R1 is always going to be taking all the current. All the current has to go through R1, and then it's going to divide up against, that current then is going to divide up against D1 and D2. So if we drew in our current path, we know that my current is going to come up. It's going to come up to my reference point. It's going to hit my first current node. 7 milliamps of current is going to go through R2. That means the remainder must have to go across my D1. And then those two currents then are going to combine together. And all my current is going through R1, which is my total current of 930 milliamps. Okay? So when I first turn on that power on that circuit, R1 is going to drop that 909.1 millivolts. R2 is going to drop 9.091 volts. And then all of a sudden that diode is going to find out that it's biasing, it's forward biasing, it's going to be a gulf. It's going to turn on, and then it's going to sink all these other voltages back down. And it's going to bring this one down to 0.7 volts or 700 millivolts. And the remainder amount of voltage then is going to drop across R1. Okay? That all make sense there? Everyone see that? All right. Any questions on it before I erase it? All good? Okay. I can zoom. Zoom in a little bit more. There's a little bit more room to see it. All right. number 2. Okay, so we got plus 20 volts. What's my first step?
Circle the active component.
Circle the active component. Then my next step. Just like all the other circuits, so we circle the active component, then what do we treat that diode as?
Open.
As an open. So we're just going to take it out of the circuit. So what type of circuit do we have now?
Series.
Series circuit. Another name for a series circuit is what?
Voltage divider.
Voltage divider. So what do we do? Divide up the voltage. So what would be my, what's my voltage across R1?
Oh, this is 20.
1.818 volts.
Say one more time. 1 point what?
818. 1.818 volts.
Okay. And then R2?
18.18 volts.
Okay. So then my next step then is going to be what? So which way is my current
South
going?
voltage.
North to south or south to north?
South to north.
South to north.
South to north, yeah. So it's going up at 30. So this helps us out because we need to use those for our soft voltages. Okay, then our next step then?
Mark the soft voltage.
Yeah, mark the soft voltages. Okay, so what would I measure for soft voltage on my anode side? One little gun sight from circuit number 1.
18.18 volts. Positive 18.18.
Positive, yes. Positive 18.18 volts. Okay, and then on the cathode side? Plus or minus 0. Okay. Diode to go or no go?
Go.
It's a go. And once we determine that it's a go, it's going to do what? Diode always does what? Always drops its 0.7 volts first. Okay? Then once we determine that diode's a go, then we have to figure out what the voltages are across the other across R1 and R2. So what's the voltage across R2?
0.7 volts.
0.7 volts. And then the voltage across R1 is going to be what?
19.30 volts.
18.30 volts. So those are no longer valid. And so my V out is going to be what?
Plus 0.7 volts, positive.
Plus 0.7 volts or 700 millivolts. 0.7 volts. Okay. And my voltage across, then we already did my voltage across R1 is 19.3, and then the current going through R1. .930 amps. Okay, and then current going through which one do you want? Current going through R2 then.
7 milliamps.
7 milliamps. And then the current going through the diode,
7 milliamps.
1.823 amps.
what is it?
1.823 amps?
No,
Yeah, that's right.
remember, so you remove, see, so you'd be subtracting
Minus 7 milliamps.
0.7,
Oh, crap.
1.923
I did that
amps.
wrong.
there you go. Now 1.923
Yeah.
amps. Yep. So that current's going to divide. It's going to come up 7 milliamps. It's going to go that way. 1.923 amps is going to go up through the diode. Those two currents are going to combine and then come back and go to 1.93 amps through R1. Oh, one thing I think we forgot to, I think they asked about the resistance of it. Yeah. What's the resistance of this diode? What's the resistance of that diode? How do we calculate out resistance?
Voltage divided by the current.
Yeah, voltage divided by the current. So what do we get for resistance then on this diode?
$364.
364 milliohms. Okay? Does yours not ask that?
No, it doesn't.
That's because I was looking at my lecture one.
No, it has.
I didn't have it, but then when I printed out my key, I see that that's listed on there.
It's power.
Power.
No, mine has power too, but mine also has the resistance of the diode. I don't know where I printed out your worksheets, man. All right, so that's fine. So let's just take a look at look at the resistance of that diode here first. What was the calculated resistance of that previous circuit, circuit 1? So what was the calculated resistance of that diode on circuit 1?
That'll be 752.7 milliohms.
752.7
Yeah.
milliohms. Yeah. So then if you were, if I didn't, they shouldn't have zoomed in so quick, but if we were to take a look at it though, this one had about half the current going through it, had twice as much as resistance, right? But when we started putting more current through it, because this diode is going to take this voltage first, and it's going to, and so the current is going to be dependent on whatever R2 is taking. So R2 has got to be a set value. So that's already a set resistance of 100 ohms, and it's got 7 milliamps of, so it's going to end up having 7 milliamps of current going through there. That's a set value. So the remainder amount of current then is always going to go through that diode, and that diode is going to adjust its resistance accordingly to make sure that it drops the remainder amount of current. So here we had less current, and it didn't need to have as much resistance. So the resistance went up on it. Here, we start driving more current.
That one's wrong. The resistance for the last circuit's wrong.
What should it be?
758.
758?
4
Milliohms.
There you go. Okay.
Hey Kurt,
Yeah.
that amps across the diode,
Yep.
you went 1.930 minus 0.7, right? For the amp across the diode. That one right there, yeah.
Yep. How did I come up with that number?
It's supposed to be 1.223, right? Because you minus 0.7 from that number? From 1.20?
No, you take 1.93 and subtract 0.7.
Yeah, I got 1.223 when I did that.
223? All right. Yeah.
Okay, no, you're minusing 0.7. You're supposed to minus 0.007.
0.007. Yeah, sorry. That's the 700, because we have the 7 milliamps here, so it's minus the 700, so that would be 0.007
Oh,
amps. Yeah, thanks. Yeah, so it should be the 0.00.
alright.
Yeah. So you can see that resistance of that diode is going to vary depending on. So it's kind of like a current regulator. It's going to adjust its resistance based on the amount of current that it needs to maintain. So since R2 is a fixed value of our 100 ohms, and we know that the voltage is going to be fixed of 7 volts, that's going to always leave 7 milliamps of current going through R2 no matter what. R1 is always going to end up dropping that 19.3 volts, and it has a fixed resistance of 10 ohms, so it's always going to make sure that there's always 1.930 amps. So that diode then has to vary its resistance so that it maintains that current going through those R1 and R2 since those are fixed. And that current will be regulated by that solid state device. So that's why we call these things active components. So depending on the amount of current going through them, and since the voltage is always going to be at 0.7, the amount of current going through that diode then is always going to vary that resistance of that diode to maintain that current that it needs. And that's why we consider these active components. They vary on the resistance depending on what the current is doing. The more current we go pushing through that diode, the lower the resistance is going to go. It has to open up. Remember, resistance is the opposition to current. So if it has more current trying to go through that diode, it has to allow that more current to go through there, so that resistance is going to change accordingly. So it's basically kind of like a rheostat. It's just kind of a variable rheostat. It'll adjust that resistance to maintain that certain amount of current going through that resistor. So internally, it's a little rheostat in there.
Chris, pass it
Yeah.
back. Email list.
Next Tuesday, I'll be in the computer room for next Tuesday. For my tech talk.
Tuesday evenings.
Oh, Tuesday evening? Yeah. We're going to be sending out, we were just talking here, we're probably be sending out an email, so we'll probably find out, but that Chuck is going to come in and he's going to start doing microcontrollers and C++ programming. So he's going to bring in some developmental boards and stuff, so we'll probably hold that class in here, so.
So you're going to start next Tuesday for sure?
Yep, next Tuesday we're planning on. Yep, you bet. Yeah, well, I remember here. So if you're interested in coming into activity night on next Tuesday, right now we're planning on having that Chuck Raskin that came in for that the electrical engineer guy that came in. He's going to start teaching programming and microcontrollers. So if you're interested in learning some programming and how to use microcontrollers, Tuesday nights from 6 to 9 we'll be here. Then I also have another guy lined up, so if you're interested in doing some Java programming, after we're done with this little series, then we'll have that, my computer science engineer guy come in and he'll teach us Java programming if you're interested in that. So, if I think it looks like Dominic has it, but Mindy's passing around and updating the email list. So if you want to get your name on the email list for our activity night, put your name on that list there. So.
I gotta do my email list again. I don't remember it.
Oh, okay.
That'll be kind of a good opportunity. Those microcontrollers are fun. All three, yeah. It's all these guys are just going to come in and volunteer to do it and stuff like that. So
The lab will still be open along with that, right?
Yep. I'll just open up the lab room. So for anyone that's interested in just working on their other projects, that lab will still be open. Yep. All right. Oh, so didn't calculate out the power of the diode. But the power of the diode on the first one was should have been what would you calculate out your power for on the diode on circuit number 1? What was the power of your diode?
Power is 646.1 milliwatts.
646.1 milliwatt. And then what was the current to circuit number 2 then, or the power of circuit 2 for the diode 1?
$1.346.
Yeah, 1.346 watts. Yeah. So when you start taking a look at the data sheets, that's going to be important to us because that's how diodes are rated. They're rated by the power. So, you know, if I had just, you know, I'd have to make sure this diode in the circuit here would have to be at least a 2-watt diode. This diode here I could get by with a 1-watt diode. So we need to be careful what that power is of our diodes, and that's how they're rated. You can either buy a 1-watt, 2-watt, 3-watt, whatever diodes, just like resistors. All right, let's take a look at circuit number 3 here. Okay, what's my first step?
Circle the active component.
Circle the active component. Put your polarities on inside there. Then my next step.
Mark.
Treat the diode as an open.
Solve the voltage first.
Yep, solve for the voltage. That one doesn't have. So let's see. Yep, they're all 10 ohms and 100 ohms. So R1 is going to be 10 ohms, and R2 is 100 ohms. So what's my voltage across R2 or R1, either one? Should be able to look at circuit number. Which number circuit should we be able to look at?
Number 1.
Yeah, number 1. So what do we get on circuit number 1 for voltage across R1?
909.1 millivolts.
What was it?
909.1 millivolts.
909.1 millivolts. And then R2?
909.1 volts.
No, 9 point.
Yeah.
Oh, whatever it was. 9. Sorry.
9.091 volts. All right. So now we do our soft voltages, and what do we get for soft voltage on our anode side? So if we put in our polarities, which way is my current flowing? North to south or south to north?
South to north.
Yeah, north to south.
Huh?
Negatives on top.
Right?
Yeah.
North to south, right?
Okay.
This is
Yep.
-10, right? Yeah, so that's more negative than, because this is, my reference point is plus or minus 0 volts. So I know that my -10 is more negative than my 0 volts. So, yep, I'm just going from north to south. So what's my soft voltage then on my anode of my diode?
Negative 9.091 volts.
Yeah, negative 9.091 volts. And then on my cathode side?
Plus or minus 0.
Plus or minus 0. Okay, so is that diode a go or no go?
No go.
No go, because I'm more negative on my anode than I am on my cathode. So that's going to be a no go. And What's the diode gonna drop our voltage?
Negative 10 volts.
91 volts.
10,
Yeah. Yep, gonna be.
yeah.
Yep, it's gonna drop. Remember, so it's gonna be the source voltage of whatever that parallel branch is. So even though it's an open, it's still part of this parallel branch. So it's gonna drop the source voltage of that parallel branch. So it's gonna drop our 9.091 volts. Okay. So then these two. So then, what's my PL going to be then?
Negative 9.91 volts.
Yeah, a negative 9.091 volts. Okay, then so what's the voltage across R1? 909.1 millivolts, that stays the same. And then the voltage across, or the current through R1.
I think it's 90.91 milliamps.
90.91 milliamps.
Yeah. Yes.
Okay. 90.91 milliamps. What's my current going through R2 then?
90.91 milliamps.
Right. Because with that diode not being in there, what type of circuit do we have?
Series.
Series. And what remains constant in series circuit?
Current.
Current. So if we know what R1 is, then we know R2 has to be the same. So even if you calculate it out, you should still calculate it out to be the same as 90.91 milliamps. Like I said, all these little simple rules, they always still apply. We're kind of continuously using them. If we follow those rules, we can almost analyze any circuit. Just following those rules. All right. So so what's my power? My power of my diode then?
0 watts.
0 watts. Do I have any current going through that diode? No. So no watts. The resistance of that, so what's the resistance of that diode then?
Infinite.
Infinite. Be wide open. Yep. Not 0, but infinite. Yep. Sometimes we get confused between 0 ohms and infinite, but yeah, it'd be infinite ohms. All right, let's see. All right, I don't know. You guys got that one down? Got those down pretty good? Tyler, we're ready to move on. All right. You got your homework sheet that you can kind of practice doing these. If you have any questions, let me know. But go ahead and practice them. All right. This next one, this is the one I should have really held off on. Wait until you guys are all nice, wide awake this morning, and this one's a little bit. This is a little bit more challenging, kind of. But once you catch on to it, then it's not bad. But when we're analyzing circuits and stuff like that, a lot of times our circuits are going to look. This is what we see in our schematic. We'd have a test point here, and then a couple of components. So we need to determine what that, maybe what test point E is. Okay. So let's take a look at the first one here. So if I have E1 as plus or minus 0 volts and E2 is plus plus 15 volts. What is EA? So what would EA equal?
Which one?
Okay, so start following your so follow our steps. What's the first step that you're going to want to do?
Circle the active component.
Circle the active component. All right. Then what's my next step? Treat it as an open. So I look at it as an open. What would I measure for? What would I measure for a soft voltage at this point?
0 volts.
Okay, so what's so like if what's my voltage at my reference point?
Plus or minus 0 volts.
Plus or minus 0 volts. Do I have a reference point on here? Yeah, I certainly do. Yep, I have plus or minus 0 volts. That's my reference point. So if I put my red lead on here, or put my black lead on my reference point, I know that's plus or minus 0 volts. Bring my red lead here, what would I measure for voltage?
0 volts.
0 volts, plus or minus 0 volts. Okay? If I got my black lead on my reference thing, this dial is acting like an open, what am I going to measure for voltage?
0 volts. Plus or minus.
Plus 15.
Plus 15 volts. Okay, so let's take a look and see why that would be. So if I really drew up that circuit, again we can just kind of draw up that circuit. So we know that this is a plus 15 volts, right? So here's what my circuit looks like. So here's my polarity of there's my power supply, right? Now it's flipped upside down, typically what we normally see and stuff like that. But if I were to apply, don't I get, referencing it to ground, don't I get plus or minus 0 volts at this test point E1?
Yep.
Yep. And what would I measure for E2 then? Plus 15 volts. It's my source. I'm just measuring across my source. So here's my source. Okay, so now if I treat this as an open, I just have a series circuit, right? Treat this as an open, referencing it to ground. That dial is going to act like an open, so it's going to measure the source voltage, plus 15 volts. On this side here, I'm going to just be measuring my 0 volts. Again, we can kind of take a look at it. Here's plus 15 volts. We know that my current is going this way, so here's negative positive, assuming that the diode is drawing current, but just to give us help us out how to analyze this. Take a look at it. If I wanted to know what this voltage was, I could go down. My first sign let's see. Yeah. That's kind of a little bit. Yeah. So that's kind of well. Starting from here, this is what my source voltage. This is what I wanted to do. Go from my source voltage here, come back up. My first sign I see is positive 15 volts, and now I'm back to my reference. So that's my source voltage is at my 15 volts. Okay? So that's what my circuit looks like. So now we know what our soft voltage is on our cathode side and our anode side. Is that a go or a no go?
Go.
That's going to be a go. And that dial is going to do what?
Drop 0.7 volts.
Drops 0.7 volts. Okay? So we know that diode to go, then we know the current going through the diode then is going from what? North to south or south to north?
North to south.
North to south. And we already kind of doing those polarities. There's our, and so then we know that all my current has to be going through that way. what's my voltage going to be across R1?
14.3 volts.
Yeah, that was going to drop to 14.3 volts. Okay. There's all my current paths and polarities. Now, what's my voltage at test point A going to be then?
0.7 volts.
0.7 volts. So here's my red lead, put my black lead on my reference, and put it here or here. Go up, my first sign I see is a positive 0.7 volts, and then I'm back to my reference. And then if I go down the other way, first sign I see is a negative 14.3 volts, come back around, and now I add it to a positive 15 volts, gives me a positive 7 volts. So no matter which direction I go, I'm always going to get EA is always going to equal, EA is always going to equal my positive 0.7 volts. Okay? So when we're analyzing circuits, you know, sometimes the schematics aren't going to give us all the information there. Sometimes it's easier, so we can analyze it, draw up what the circuit is. Okay? Alright, so let's take a look at another one here.
Tom's making faces in the window.
Huh?
Tom was making
Tom was?
Yeah, he's taking a note.
He's got a smudge mark on the window.
Alright, so what would be my voltage at EA then?
I'm gonna have to draw this.
Negative 10 volts. Everyone see it?
Yes.
Okay, so let's draw up our schematics. We know that this is my reference point, right? We know that my source has to be a negative source. Okay, so here's my source, 10 volts, negative positive, and here's my reference point. Okay, so that would be my circuit now, right? Because referencing it from here to my reference point, if I bring my red lead around to my black lead, first sign I see is going to be negative 10 volts. Okay? And we know that this is at plus or minus 0 volts, so we know that's my reference point. Okay? So we know we have 10 volts there. So we still circle the active component. Treat it as an open, right? So we do it as an open. So what would I measure for a soft voltage on my cathode side? Plus or minus 0. And then on my anode side, negative 10 volts. Okay? Is that diode a go or no go? No go, right? I'm more negative on my anode side than I'm on my cathode side. So that's going to be a no go. And if it's a no go, it's going to drop what?
Source voltage.
Source voltage. So the source voltage is going to be my 10 volts. So we know that this is my negative side of my source. So if I did have current going through it, my polarities across my components are going to be negative, positive, because we already determined that this was more positive, more negative. So we know that the current would have been that if it was drawing current. So that would be my current path if I had current. So then if I put my red lead on A, put my black lead on my reference point, first sign I see is negative 10, and I'm back to my reference point. If I go the other way, this is going to drop. What's R1 going to drop in voltage?
0 volts.
0 volts. So then if I go the other way, first sign I see is positive, 0, plus, a negative 10. Okay? So EA then is going to equal to negative 10 volts. Okay? And just that logical thinking, we're just trying to get your mind into how to logically think through these circuits. All right, any questions on that one? Pretty straightforward? All right. All right, we'll change her up a little bit here then. What's the EA? No, it would be 12 volts.
7.
7 volts?
That's 7 volts.
0.7 volts.
Not 0.7 volts. Not negative 12 volts.
Oh. $11.3 volts?
What did you say?
11.3?
No? Sometimes it's easier just to analyze it than it is to guess. There's a lot of numbers between infinity, negative infinity, positive infinity. A lot of numbers in between there. All right, let's analyze this thing. All right. So so let's take a look. Let's go ahead and let's just draw up the circuit so we understand what the circuit is. So we know that we have to have a positive 12 volts here, right? So we know that we have a 12 volt source, right? So we got so we need to know, so we know for sure that we have to have a 12 volt source on there. Then we also know that we have a 5 volt source on there. So let's draw up a power supply for the 5 volts. All right, so far there, right? So there's my, so now where would I have to have my reference point then to get my positive 5 volts here and my positive 12 volts there? I'll give you a hint, it's the only line I haven't connected yet.
In the middle. Between the sources.
Between the two source voltages, right? So if I bring there and I bring out my ground there, if we double check our work to make sure that we do actually have what we said, here's my reference point, right? Here's my red lead. I want to make sure that I do have positive 5 volts at E1. Bring my red lead over. First sign I see is positive 5 volts and I'm back to ground. So I got a positive 5 volts there. Now, I come over here, go to E2. I want to make sure that I have a positive 12 volts. Bring my red lead over. First sign I see is positive 12 volts. So there's my, so now I know that I've confirmed that that's my circuit. Series aiding or opposing power supplies.
Opposing.
Series opposing power supplies. Okay? See that in op amps all the time. Alright. So now, let's go through the process of what we call our rapid circuit analysis procedure and follow those procedures so that we can analyze this circuit. So what's the first step I want to do?
Circle the active component.
Circle the active component. Put my polarities inside there. Then what's my next step? Get my soft voltages, right?
Yeah.
Okay, so put your black lead on your ground, put your red lead on your either side, doesn't matter, we'll start out with the cathode. So what would I measure for voltage at this point here?
5 volts.
Positive 5 volts. Okay, then on my anode side, what would I measure first? My source voltage. Positive 12 volts. Okay, so is that a go or a no go?
No go.
That's a go.
That's a go, right? Because my positive 5 volts is more negative than my positive 12 volts by 0.7 volts. So that's a go. And then the diode's going to do what? Take its 0.7. Okay? So then, I only have 2 components in the circuit, right? So what's R1 going to drop for voltage then?
The remaining 6.3 volts.
Yeah. So because so the difference between my positive 12 volts and my positive 5 volts, what do I have for a voltage potential between those 2 points? 7, right? So I got my 7